Hi everyone, and welcome to our tutorial on event-centric natural language understanding. I'm Dan Roth, and I'm going to give this tutorial together with my colleagues Muhao Chen, Honming Zhang, Qiang Ning, Mengling Li, and Hang Ji. So why do we want to talk about event-centric natural language understanding? Well, we think that the time is right for that. After all, natural language is really there in order to describe events, to reason about events, to communicate about events. So you can look at the paragraph that I put here on the top right, describing events related to the recent riot on the US Capitol. And you can agree that, really what we use language for is to describe what has happened and perhaps what could have happened or what may happen, to reason about who did what to whom and why. We use language to understand what might have led to what caused what. And we often describe an hypothesis about events, about feelings relative to events, about plans. And you can think about it in the case of news, you can think about it in the context of very different types of events. This is a recap of a football game that happened yesterday. And in all these cases, we really use language in order to discuss and communicate to others our thoughts about events. Now, we describe events at very different level of abstraction. Here is one single event that is described in 6 different ways, different level of abstraction, different level of details, for different purposes, to convey different messages, perhaps to different readers. But you can also think about describing events at very different levels of granularity. So the event of Napoleon invasion to Russia, which took months, is described here in one piece of text over a map, and at a very, very high level, from causes to what caused it to fail. And you can also think about a range of goals in mind when you describe events, from surveying what has happened, to analysis of what has happened, up to trying to predict what could happen, for example, in 2021. So we think that the time is right to think currently about event-centric natural language processing. Most of the work in NLP so far and today really focuses on understanding what the text says. We analyze sentences. We want to understand what's written here. And more we try to understand what's written at the document level and even across document level. But with the level of progress in understanding what the text actually says, we want now to attend to what is happening and understanding what is happening. And again, you can think about what is happening with multiple purposes in mind, from just describing what is happening, analyzing what is happening, and perhaps predicting what may happen in the future, given what we've learned from the past. So what does it entail to understand what is happening? This is really what we want to focus the tutorial on, and what kind of NLP should we develop in order to understand that. So event-centric natural language understanding really brings some change in foci and in priorities. Of course, it requires that we understand locally the text, but beyond that, it necessitates that we integrate information from multiple documents and modalities. We should be able to aggregate information and consolidate information from multiple sources and from different ways of presenting things. We should be able to understand multiple types of events, understand relations between events, understand time and causality, be able to acquire background knowledge that is essential to understand what is happening, as well as common sense knowledge that is often required to understand even what the text says. It requires the ability to generalize from specific observed processes to more general principles, and it requires the ability to predict implicit events that are very important to understanding what is happening, and possibly also future events. Eventually, it will also require us to identify that stories can be told from multiple perspectives. They could have multiple interpretations, and we should be able to attend to these two, and perhaps also to issues such as trustworthiness of the sources. And of course, we should be able to integrate all these into an understanding of what is happening. So as an example of perhaps a dream that we would like to achieve with this line of work, let's think about compiling a history book. Ideally, again, when we compile a history book, we want to be able to do it at multiple levels of granularities, and we want to be able to account for multiple perspectives and multiple interpretations. So given what has happened in the US in recent days, what's a better topic than to think a little bit about the history of democracy? And I'm going to start and talk here about the French Revolution a little bit, partly because this is an event that was definitely impacted by the US or the American Revolution in 1776. So you can think about the way to organize it as a flowchart. When you extract a lot of events, you abstract them into short descriptions, and you have a flowcharts along with arrows that indicate the influence. Perhaps you want to even have arrows of multiple types, and I'm going to attend to it a little bit later. So in this case, this flowchart describes the roots of the American Revolution. And you can see that there are some interesting events that people have attributed to as part of the roots of the American Revolution. For example, the literacy rate grown up significantly in the 1780s. But you can also think about what about the role of the rise of the democracy in America? What impact did it have? And this author here actually downplayed this a little bit. Perhaps you can put it into the box of spread of Enlightenment ideas and liberty on liberty and democracy. But you know, some other historian would tell you that Americans' victory over the British really has been the single most important impactful event on the French Revolution, and that the newly formed government in the United States really became the model for the French reformers. And this gives you the idea that, you know, interpreting event could have multiple perspectives. But we can go ahead with the French Revolution and think also about the start of the French Revolution. What were the events that started this French Revolution? And you can organize them again as a flowchart and think about the various events at different scales that led to this. You can also think about, in more details, the course of the French Revolution from 1789 to 1781, and think about specific events that happened there. Again, all these is a collection, aggregation of historical evidence, everything written in text that has been compiled to this flow of history that we can see here. We can dive in more details into specific events within the French Revolution, or we can move to studying the results of the French Revolution. And again, there is no debate that some of the results here have to do with liberty and equality, or increased liberty and equality. But some would argue that this also resulted in increased nationalism leading all the way to the First World War. And you can also move one level up and think about the role of the French Revolution as part of an age of revolutions that occurred during this time. What is the place of the French Revolution in the bigger picture? Altogether, this gives you an idea of what might be achievable if we are able to process text at this level, relate events, analyze events, and discuss it. Now, you can take another view of this and think about the timeline. So not only do I want to understand causes and effects, I want to be able to place them on a time. And I can attend here also to the notion of links between events. So links between events could be influence, but you could also refine this a lot more and think about influences that are a cause of natural events or processes, or those that indicate technological developments, those that indicate cultural developments, military and political developments, and so on. And of course, you can show a timeline of the whole process, or you can dive in and look at a finer timeline that shows specific event day in the course of this set of events. So all these is so far at a level of a dream. It's really challenging to compile such an account, even given, in retrospect, given a lot of historical text, and even more so if we want to do it from reported events as things go on, as we would like to do. So this leads us to the goal of this tutorial. So what we want to do is we want to be able to address all the technical issues that the community has addressed over the last few years, and of course, get also into the challenges that we want to address. So the starting point for this is to think about single events. We want to be able to define events, think about representation of events, and extract events and their arguments. Of course, we want to go beyond understanding single events. We want to think about hierarchies, event schemas, and relations between events, leading eventually to depicting event this way, where we have high-level events like a coup, sub-events of the coup, participants, relations between them, understanding the topics of each sub-event, and so on. And of course, we want to be able to understand relations between agents, relations between other arguments, relations between attributes of events, and relations between events, as well as properties, temporal property of events, duration, frequency of events, absolute times, and so on. So the next step from event extraction is going to, and of course, we want to do this in multi-modal way. A lot of information about events can be extracted from images and videos, and we want to be able to not only extract events from these other modalities, but also integrate it along with the text. So the next step beyond extraction has to do with understanding relations between events. We have to understand that there are various types of events. Some events actually happen. Some events are only expressed as intentions or plans or attempts. And this understanding is essential if we want to think about relations between events, because if events belong to different types, some are plans and some are actual, perhaps we cannot compare between them or study relations between them. So we want to study temporal relations between events, but we also want to study relations such as parent-child relations and co-reference relations. And of course, we're going to address some of the techniques that people have developed over the years in order to develop these technologies. Moving from relations, we can now think about processes of events. Of course, events are not isolated, and quite often we want to think about a sequence of events. And there are multiple questions we can ask in this context. If you want to perform high-level events like buying a house, you can ask the questions of how to do this task. What are the sub-events that constitute buying a house? You can also think about the inverse operation where you observe multiple events and you want to know, okay, so what is the overall process here? What are they doing? And of course, we want to be able to think about in the context of narratives, narrative development, narrative understanding, and potentially also predicting the continuation of narratives. In order to address all these questions, we need to acquire background knowledge that is relevant, and we need to acquire common sense knowledge that is relevant. And we're going to discuss some of the knowledge sources that are important to facilitate reasoning about events, from those that are important to understand relations between events, what might have happened before, what could happen in the future. We want to be able to understand common sense aspects that are related to events. For example, what is a typical time of this event? What is the typical duration of this event? What is the frequency of this event? And so on. So temporal common sense is going to play an important role in understanding this. And with all this, we're going to address also some of the challenges that we want to face in this case. So to summarize, this is what you're going to see in the next 2.5 hours. After following this introduction, we're going to start talking about event-centric information extraction, moving to understanding relations between events, and after a short break, discussing processes and discussing knowledge acquisition and common sense reasoning. And toward the end, we're going to talk about some future work and dreams in the domain of events. So with that, let's move on to the rest of the tutorial. Thank you.
Hi, this is Manling from UIC. I'm currently a PhD student working with Professor Heng Ji. Thanks for listening to our tutorial. I'm presenting the first technical part about information extraction in event-centric natural language processing. The definition of events is broad. For example, events can be momentary, like sneeze. It can also indicate something that happens, like running. In natural language processing, we focus on specific events that trigger a change of status. I will introduce event extraction following 4 parts. Firstly, when we have training resources, we can learn to extract events in a supervised setting. And then we can extend the event extraction to new domains, languages, and data modalities. Information extraction aims to extract the structured knowledge from the unstructured data, so it's a structured prediction task. Here in event extraction, the structures contains 2 parts. The first part is the event trigger and also the event type. The second part is the event arguments, so it builds an edge between the trigger and entities. The knowledge can be in any data type, and also the unstructured source data can be in different domains and different languages and also different data modalities. In old days, what we normally do is spending a few days to carefully design the symbolic features for each task. Different tasks like entity extraction, relation extraction, and event extraction will need their task-specific subset of features, tools, and resources. The good thing is that this feature engineering is expandable, and we can see which feature helps which task. However, it's time-consuming, and we need to redo the entire process for the new task. To reduce the human effort, modern methods throw away symbolic features and use embeddings instead. For example, here, STM and CNN are used to encode the context. Also, symbolic features are added as additional features by concatenating them with word embeddings, such as the entity type, dependency tree relations, and so on. However, these frameworks cannot handle the errors propagated from entity and relation extraction, and also the interdependencies between knowledge elements are ignored. For example, the election event should always have only one person argument. And also in the meanwhile, this person argument is not the same person as the resigning event. Our recent work, 1IE, is an end-to-end neural model to jointly extract entities, relations, and events. So it outputs an information network instead of separate knowledge elements. This model firstly encodes the tokens in the input sentence and then decode a graph directly. In this graph, each node will be an entity or an event, and the edges will be relations or event argument rows that connect these entities and events. It can be extended to other languages using multilingual BERT, since it does not rely on any symbolic features like dependency parsing. In this work, we also use symbolic features to incorporate high-level global knowledge. For example, when we do event detection, it's really important to understand what happened in the past, because history always repeats itself. So maybe from millions of historical events, we can learn some global patterns. We call these global patterns as event schema. And this is an example of civil unrest event schema. It models the interactions between knowledge elements. For example, here, after public speaking, there will be social gathering event. And also the audience of the public speaking event is the person that participate in the gathering event. So these arguments are also connected. To induce this kind of event schema, we use templates to explore the interactions between knowledge elements. For each template, we fill in all possible types to generate a set of global features. For example, here the first feature means that an entity is a victim of a die event and a target of an attack event at the same time. The second one is similar, where the person entity is the attacker, which is usually not true in the training set, except for the suicide cases. In this way, the model learns that the first one is the positive feature, and the second one is the negative feature, and it can promote information graphs containing the first structure and demote the graphs matching the second feature. The schema library can be further extended. Our work on schema induction using path language model extends the library to longer paths between events. After that, we let the model learn the weight of each feature automatically and add the weighted score into the local type prediction scores. So this combined score is used in the beam search to decode the graph. In each decoding step, we generate one node and predict the edges between that node and also the existing nodes. So in the node step, we predict the top k node types for the new node. And in the edge step, we predict the top k edge combinations with existing nodes. Then all candidate graphs are generated and will be ranked based on the combination of local scores and global scores. The local scores help to select the best type prediction, and the global score promotes the graphs that matches event schema. For example, here are two candidate subgraphs. The first one may have a higher local score, where it predicts the organization as the entity of the fine event. It's not true in most cases. And this model can demote this candidate graph with global features that evaluate such structures. And in this way, the model can know that compile is a person instead of facility, since it's the entity of the fine event. This model outperforms the state-of-the-art end-to-end IE model on most subtasks on ACE 2005. The experiment results also show that this model can be easily adapted for other languages, such as Chinese and Spanish. Since the model feature is independent of language, so adding English data can further improve the performance on Chinese and Spanish. Sentence-level IE ignores the arguments from other sentences. So recently, there are work extending the sentence-level IE to document-level IE. The basic idea is to link the argument rows to the text dimensions. The linking is also based on the contextualized embeddings. To get the embedding representing argument rows, the trigger embedding and row embedding are combined as the implicit argument embedding. Then for this trigger, the embedding is further compared with the text argument representation using a linking score function. Considering that the searching space of arguments is huge when the document is very long, then a prove function is learned to select top k candidate arguments for each trigger. To avoid the error propagation from entity extraction, a new question answering-based paradigm is also proposed. Several question templates are predefined for each event type, and each input sentence is mapped to the standard BERT input format using the question templates. The extraction is done by two BERT-based QMA models, one for event trigger detection and another one for argument extraction. In this way, trigger detection becomes a request to identify the action or the verb in the input sentence and also determine its event type. The argument extraction becomes a sequence of requests to identify the text spans as arguments, so the extraction process can be treated as generating answers to machine reading comprehension. Okay, now the success of supervised model for one domain. How can we transfer this knowledge to extract events in a new domain with completely new event types? If we perform AMR parsing to the input sentences, we can see that a trigger and its event type label usually have some shared meaning, and their structures always tend to be similar. As a result, we model event extraction as a generic grounding problem by mapping each mention to its semantically closest event type. For example, the trigger fire can be grounded to attack event, and also the dispatching can be grounded to transport person event. Given a target event ontology, the goal is to learn a generic mapping function, and this mapping function should be independent of event types. It can be trained from annotations from a limited number of seen event types, and then used for any new unseen event types. So what we do is jointly represent and map event mentions and types into a shared semantic common space. For event mention with unseen types, their structures will be projected into the same space using the same framework, and then the types are assigned with the top-ranked similarity values. To construct a common semantic space, we minimize the distance between each event mention and its corresponding type. For example, the representation of fire is optimized to be close to the representation of event type attack. This knowledge can be transferred from existing types to the extraction of unseen types by projecting the unseen types to the same shared common space. Without any annotated data, the transfer learning approach achieves performance comparable to LSTM trained on 3,000 sentences with 500 annotated event mentions. It shows that the success of this transfer learning framework for new event types. To summarize, for any new unseen event types, this model can only take the ontology definition of the unseen event type, like its type name, and also its row names for its arguments. And also, it needs some annotations for one or few seen event types, then it can perform event extraction for the unseen types. However, event type is not the only informative part for event definition. There are also definition sentences and a set of argument rows and the event type constraints for these rows. To fully represent the semantics of labels, instead of using single words or single embeddings, the labels are represented as a cluster of contextualized embeddings. For example, each small node here is a contextualized representation of event label, say attacking event. And by analyzing the distribution of these representations, we can easily get the cluster of this event type. We use this green circle to represent the cluster. So if a new trigger comes in, and if its representation appears inside the circle, say the blue node, we assume it belongs to this type. Otherwise, like the red node, we assume it's not this type. After this initial prediction, we can leverage the entity type constraint and model the final prediction as the LP problem. Okay, so here is the details about the overall proposed framework. It consists of two parts, the offline preparation and the online prediction. In the offline preparation phase, for each predefined event trigger or argument type, we first find some anchor words. These anchor words are basically the labels themselves or the synonyms of these labels. After that, we find several contextualized usage of these words in the external corpus, like New York Times corpus. We call these sentences as the anchor sentences. For each of these sentences, we can get a contextualized vector for the anchor words, and then based on all of these vectors, we can get the event type representation in the embedding space. During the online prediction phase, given an event, we first acquire its contextualized representation for all trigger and argument words, following the same way we did for the labels. After that, we find their position in the embedding space and make the prediction accordingly. On top of this initial prediction, we involve the constraints from the event definition to regularize the final prediction. Additionally, we use two different representation methods for triggers and arguments when we generate embeddings. We do not have any masking operation when generates the embeddings for triggers and trigger labels. So basically, we input the entire sentence and select the representation at the corresponding positions. However, for arguments, we use masking strategy to mask the target argument and only use the context to generate the representations. The motivation is that most triggers contribute the most important semantic meaning, while the semantic of arguments are often inferred from the context rather than from the argument themselves. For example, many arguments are pronouns or names, which only have weak semantics by themselves, and we do not need to understand them by understanding their context. So here are the classification results. We did the experiment on ACE 2005. To compare with previous work, we showed the performance on two settings. In the first setting, we only evaluate the least 23 frequent event types, and the results show that this system actually performed very well. In the second setting, which is the entire dataset, the model can correctly map more than 80% of triggers and more than 50% of the argument to the correct type. This result is actually very encouraging and shows that it's possible to only leverage the semantics of the labels to make prediction. Experiments show that the example sentences, we can only use 10 example sentences to get this performance. One explanation is that the event labels are carefully selected by experts. So the semantics of a predefined event type should be the same as the most popular meaning of the label word. As a result, even though the label words may have multiple semantics, we can always get the most popular meaning by the average of few anchor sentences. Okay, now we know how to deal with new event types in new domains. Let's talk about cross-lingual transfer. There are around 300 languages in the world, and most of them are low-resource languages due to the difficulty of IE annotation. So it's important to perform cross-lingual transfer for these low-resource languages. The first step is to build a multilingual common space. One thing we noticed is that entities are very different from words. If you only use regular word embeddings, you won't be able to distinguish these entities from words, and you also won't know how to put several tokens together into phrases. As a result, we take advantage of Wikipedia, the multilingual encyclopedia, and we replace the entity text with its anchor link in the Wikipedia. For example, the word apple here is replaced with the Apple Incorporate entity in English Wikipedia. In this way, we can use these entities as anchor nodes to map the Chinese embedding space to English embedding space. The same process can be applied to any languages. So the space of any languages can be mapped to the English space. Then we can have a nice multilingual joint word and entity embedding. A common space is not enough for relation and event extraction because relations and events usually involve wide context. So you need to figure out how these entities are connected to each other and how the entities and the event triggers are connected to each other. For example, here if you look at this English sentence and also this Russian sentence, you can clearly see that the subtree covering the trigger and arguments almost look identical. So even though their word orders might be different, but their local structures will look very similar when they are involved in the same type of relations and events. So this encourages us to convert the sentence to a dependency structures. And the reason that we use dependency structure because the nice universal dependency parsing community has already developed the universal dependency parser for more than 70 languages. After dependency parsing, we can use one graph convolution neural networks to map the graphs of different languages into one common space. Each node will be initiated using multilingual joint word and entity embedding, and will incorporate the information from its neighbors based on the graph neural network. Then we can train a model for structured prediction. For example, we can consider event argument row as an edge between an event node and an entity node. We can train the model using English training data and apply it to other languages. For example, we apply this trained model from English to Chinese, and we can get almost the same performance compared to a supervised model. This supervised model is trained on 3,000 Chinese event mentions. So from this, we can know that we can use this idea to reduce lots of cross-lingual transfer costs. Okay, this is about cross-lingual structure transfer. Inspired by this great success, we try to use the similar idea to cross-media transfer. Nowadays, news are presented using multimedia data, and the information from text and image are complementary. For example, the stretcher used to move soldiers is not explicitly expressed in the text, so they can only be extracted from image. However, most work on event extraction focuses on text side, ignoring information on the vision side. As a result, we propose a new task called multimedia event extraction to extract the events and their arguments from multimedia documents. The input contains a text article and the images associated. Each output event and the argument can come from either text or image or both of them. In this example, the trigger word deploy and the image are about the same transport event, and the agent, destination, and the artifact arguments can be extracted to text, but the vehicle can only be extracted from the image. There are some work in computer vision community to extract events, but they are from different angle and they focus on physical events in daily life scenario, like jumping, clipping, this kind of simple activities. So it's not. So it has a gap with the complex events in the traditional text event extraction. The traditional text event extraction extracts complicated events like transportation, protest, and so on. But the good news is that some work offers resources similar to event argument extraction. For example, in situation recognition, one image is classified to a verb, and it populates a table with nouns as arguments. But different from our task, it does not localize arguments in images. To perform multimedia joint event extraction, the key step is to understand the semantic structures of both modalities. If we consider vision as a second language, similar to multilingual common space, we can construct a multimedia common space where text and the image can be aligned through multiple levels. For example, the entity in the text can be aligned to visual objects, and the event triggers can be aligned to visual activities. So similar to linguistic structures in text, we want to find a semantic structure from image that can be aligned. On the text side, we extract the AMR graph, which is a graph constructed by predicates and their arguments. On the vision side, we mimic it by representing an image as a predicate node. It shows the situation of the graph, that is to say, it shows what is going on in the image. And we connect this image node to the objects in the image. So these object nodes are the potential arguments of the predicate. And we call it situation graph since it shows the situation of the image. Once we have these two graphs from text and image, and these two graphs are kind of carrying similar semantics, we can develop a joint training framework to encode these two graphs into a common space. And in this common space, the nodes with similar semantics are close to each other. For example, through from the image and a tag from the text are close to each other since they are referring to the same event. Since we use publicly available AMR parser to generate AMR graph from text, the main question in this framework will be how to generate the situation graph and how to build the common space. To solve the first question, we develop two methods. The first one is object-based graph. We apply an object detector to extract the objects and apply CNN to extract their features. And then we use a projection layer to map them to word spaces. So the projected image is optimized to be close to its situation verb. Similarly, objects are mapped to nouns. Then we apply a role classifier to determine the role of the objects. This method is limited to a predefined object class ontology. So if an object cannot be detected, then we will miss it as argument. In order to solve this problem, we propose role-driven attention graph. We apply attention mechanism to localize each argument role in the image, and each entity has a localized feature vector, and we can project it into the word space. This method increases the recall by extracting arguments not covered by the object detector, such as the stones and bombs. But the drawback is that it cannot generate precise bounding boxes. To answer the second question about how to construct multimedia common space, we apply graph convolution networks to project nodes in the graph into our common space. To train such graph convolution networks, we use image caption pairs. Traditional crosslingual alignment uses triplet loss to minimize the distance between image vector and caption vector. It cannot capture the structured information, so we learn the cross-attention between image graph nodes and text graph nodes. To optimize the cross-attention, we reconstruct the text vectors using image nodes, and we minimize the distance between original and reconstructed text vectors. Similarly, we can optimize the cross-attention in a reversed direction by reconstructing the visual vectors using text nodes. With this situation graph generation and common space construction, given any image and sentence, we can represent them using multimedia common representations, such as the yellow nodes from the text and the blue nodes from the image. Since these nodes are in the same space, we can use the shared classifier to classify them from both modalities. The text and the image event extraction are two training tasks using different data. So we use ACE data for text and use situation recognition data for image. But they optimize one shared event and argument classifier simultaneously. The training does not need any parallel data. The magic here is that the cross-media alignment uses image caption pairs to train, and we crawl a lot of image caption pairs from VOA websites. These image caption pairs comes for free, do not need any annotation. So we call it weakly aligned structure embedding framework. After training, we can process a real multimedia document. Given one sentence and one image, we can pass them into graphs. Since they are in the same common space, we average the representations of trigger and image to predict the event type jointly, which is more accurate than predicting each modality independently, and we prove it in the experiments. In real multimedia documents, there are multiple sentences and images. We encode them into one common space and compare them using the alignment laws to decide whether the image and sentence are about the same event. We merge the argument of coreferential events, and these coreferential events has a constraint that they should be in the same event type. So the framework here is flexible. We can input either text or image or both modalities. And the output will be events with arguments from the same ontology. In the experiment, we separate the annotated events into text-only events, image-only events, and multimedia events based on whether the event is corresponding to a text trigger or an image or both. Multimedia setting covers arguments from both modalities, so it makes the task much harder than text-only and image-only. Our multimedia system outperforms the system trained on only text and image. Also, the structured common space of two versions, object graph-based version and attention graph-based version, they both achieve significant gains compared to flat embedding. Cross-media event coreference is also improved by the structured common space, since our alignment method considers the semantic structures of both modalities. These are some examples showing how image and text help each other. In the first example, the system detected it as a protest event, since the visual features of celebration and protest are very similar. However, with the surrounding text, the system knows that it's not the protest event. In the second example, if we only look at the sentence, the word search is not be able to classify it as a arrest event. But with the image clearly show that there is an arrest event, the search can be extracted as arrest from the text side. One interesting discovery is that not only multimedia events benefit from multimedia training, but text-only and image-only event extraction are also improved. For text-only events, the semantics of triggers varies largely in different contexts. For example, these four sentences all mention arrest event, and they have completely different context, but the corresponding images are similar. So when we learn a common space, these images will act as a hub that can pull these text sentences close to each other. But in the text-only training, we don't have this image caption alignment, so these text sentences will remain far apart, and this will be harder for the system to classify them into same event type class. Compared to cross-media flat embedding, our structured common space can capture the connections between visual objects. In the first example, the person in the middle is always the entity being arrested, but not the agent of the arrest event. To summarize, there are two main goals for information extraction system. One is quality, so the system has good performance. Another one is portability, so the system can be applied to new domains, new languages, and new data modalities. Supervised IE models achieve good quality, but suffer from the low portability. Weakly supervised methods improves the portability, but the quality drops a lot. Now, with the knowledge of schemas, both quality and portability are improved. This is the presentation of the first part. Thank you for listening.
Hello everyone, I'm Qiangning from Amazon. I'm going to discuss event-to-event relationship extraction in natural language processing. So far, we have seen how event is defined and represented in the previous part. We must see that events are not isolated, and there are various types of relationships between them. For instance, there are coreference relationships, temporal relationships, parent-child relationships, and also causal relationships. Here is an example. Chipotle is held virtually due to the pandemic. Its attendees are thus giving remote presentations of their research. These are all of the events highlighted in this sentence. And for instance, there is a relation that the pandemic causes held virtually, and held virtually causes giving remote presentations. This is referring to the conference being held virtually, which is Chipotle in this case. And giving remote presentations is a sub-event of it, which is Chipotle. And next is the temporal relation held virtually actually happens during the pandemic. Another temporal relation, their research happens before giving remote presentations. So these are a bunch of relations in various types. And these event-event relationships are often the key for understanding stories. The same event can tell a different story if their relations are different. This is a passage we just saw, where I want to highlight two relations. Held virtually causes giving remote presentations, and their research happens before giving remote presentations. Note, purely based on this passage, the research may have happened before the pandemic started. We just don't have enough information about it. In the next passage, this is a new passage, we can see the events are almost the same, but the story is different. This new passage says, Chipotle is held virtually because it has received many requests to give remote presentations. Many have also reported unexpected delays in their research during the pandemic. The story is different because it tells us that it's not held virtually causes remote presentations, but the fact that people want to give remote presentations causes held virtually. In addition, this time, we are sure their research happens during the pandemic. So these are the new relationships in this new passage. Now that event-event relationships are important, here's how we define the problem. Given a piece of text and the indicator of two events, which you may remember from our previous speakers, that is often the head phrases of these events. So the task is to extract the relationship between these event pair. Most works focus on one type of relationship. For instance, only do coreference or only do temporal relations. But nothing prevents one from predicting multiple types of relations at the same time. Since this is a standard relation extraction task, one can use precision recall to evaluate one's system performance. Another setting, probably more complicated, is to present many events. And instead of looking at one event pair, this time one can look at all event pairs in the given context. Since these relations connect many events together, we can consider multiple events and their relations jointly. There are also corresponding metrics like B3, MUC, temporal awareness that consider global coherency. Of course, there are also many works discussing these metrics and how to improve on these metrics, although they are not covered in my talk today. Finally, since in practice we are not given these events a priority, we need to extract the relations as well as those events in the first place. And naturally, there are works solving this problem jointly and applying metrics that consider event extraction errors as well. Above is what I will discuss today. There are arguably other tasks such as story close, script learning, schema induction, timeline construction, that can also be considered generally as the relationship between one single event and a bunch of other events. But those tasks will not be covered in today's talk. Speaking of event-to-event relationship extraction, there are several challenges. First, events are interrelated due to the transitive property of all kinds of relations. For instance, for coreference, if event A is equal to event B and B is equal to C, then event A must be a coreference of event C as well. When we are handling temporal relations, if A is before B, B is before C, then the transitive property of temporal relations tells us that A must be before C as well. So on and so forth for parent and child, and for causality, we have a lot of similar transitive property for these relations. Note for causality, I put a star sign after the transitivity property. That's because, strictly speaking, in that case, A is not the direct cause of C in the literature of causality discovery. But in NLP, we're typically not very rigorous here. This is still an example for the transitivity of causal relationships. Below there, that's a real example from temporal relationship extraction. We can see the complex structure when these events are connected by many temporal relations. The first challenge is still about a single type of relationship. Here, the second challenge is that there are also many cross-relation type connections. For instance, if event A is a coreference of event B, the other relationships of A must be the same of those of B. And also, if A is a parent of B, then the time span of A must include the time span of B. Finally, physically, a cause must be temporally before its effect. So these are the cross-relation type properties regarding coreference versus other relationships, parent-child relationship versus temporal relationship, and also causal relationship versus temporal relationship. This is also a real example. Chipotle is held virtually due to the pandemic. And we know the pandemic causes held virtually, so the pandemic also happens before held virtually. This is a real example of causal relationship versus temporal relationship. The third challenge, which is often more and more nuanced when we dive deep into a problem, is from events themselves. Events have many components like agents, locale, time span, and so on and so forth. And they can also have different modes like negation, uncertainty, hypothesis, repetition, and genericity. This challenge is a little hard to explain in a short tutorial, but I will try my best and give a couple of examples. Hopefully they will help. For instance, researchers went to New York to give presentations at AAAI in 2020. This is a very well-formed, unambiguous sentence. And we know to give presentations is a cause of went. And give presentations happen after went. However, shouldn't the cause event happen before the effect event? This is what we know physically, but this is obviously violated in the definition of this example. Of course, one may quickly come up with an explanation for this, but in practice, or at least in my experience, we often end up seeing too many corner cases like this and having a hard time fixing these issues in one's linguistic theory. Here is another example. He used to take a walk after dinner. And the second sentence is, he took a walk after dinner today. In both sentences, walk happens after dinner. But are they the same relationship? This is a very interesting question. For instance, if we just see another example, he used to take a walk after dinner, but today he took a walk beforehand. What's the relationship between dinner 2 and walk 3? We will come back to these two examples later, but the point here is, due to the complexity of event components and event modalities, we see many exceptions. How to design an elegant formalism with few exceptions is often the most difficult part in solving event-to-event relationship extraction. Okay, this is a quick recap for all of the challenges. The three challenges are: first, events are interrelated due to the transitive property of relations. Second, different types of relations are also interrelated. Third, event itself is a complex concept with many components and can have different modalities. I think to handle these challenges, a keyword in existing works is joint. That is, taking into consideration the structural constraints among multiple events, cross multiple relation types, and taking into consideration the event properties and event extraction. So these are the three dimensions that existing works are moving forward along with. To consider multiple events, people are considering the transitive properties in all types of relations, which we just described before in coreference, temporality, causality, and parent-child. Regarding multiple relation types, people have to consider their connection across different types of relations. For instance, the implication of coreference on other types of relationships, the implication of causal relationship on temporal relationship, and also parent-child relationship versus temporal relationship, so on and so forth. And regarding event properties and extraction, people typically handle two questions. One is how do we define events? Two is how do we joint and extract events and relations? This is a non-exhaustive overview of all existing works. And I'm also using T, C, E, P to represent temporal, causal, coreferential, and parent-child. In the early days, there are works that is very basic. And later on, people are moving along and moving forward along different dimensions of these things. For instance, work along event properties, and also work on temporal relationship extraction by considering multiple events. And also on coreference relationship extraction by considering multiple events, and so on and so forth. There are also work that considers both multiple events and also multiple relation types, which is highlighted in orange here, which is a combination of yellow and red. And of course, there is also a combination of red and blue that is considering both event properties and also considering multiple events in the same task. And these are a bunch of examples. There are two works I'm highlighting here with stars. That's because those two works are actually trying to use coreference information for event extraction, not the other way around. But I'm still listing all of them here just for your reference. In general, the general methodology is first, we want to find extractions in data or in the task, and also enforce strictly or loosely to enforce the structure either in inference or in learning or in both. And finally, to handle the difficulty in definitions, we often need to investigate the underlying linguistic formalism involving those events. I really want to mention that this is just a summary from NLP's perspective. If one views everything from machine learning's perspective, then one may talk about how do we use neural structures, how do we represent events. It will definitely be a different story. But still, I'm going to review everything from NLP's perspective. Let me take one example to explain how these structures are enforced in practice. This is a temporal graph we just saw in earlier slide. Assume that we are looking at ripping, cascaded, and ordered. We are only looking at these three events. Then because ripping is included in cascaded, it's inside cascaded, and also cascaded is before ordered, then the relation between ripping and ordered must be before. One way to take this constraint into account is called global inference, which is to respect these transitive constraints in one's inference. That is, assuming a model is already trained, then for a pair of events, the model will predict the confidence or softmax score for each label. Based on these confidence scores, we solve for the final temporal graph. Here is a toy example for how we solve for the final graph. The naive way is to select the best score for each edge, and then we get a loop. However, we know time cannot be a loop. That is also the implication of the transitive property of time. So how should we avoid this situation in practice and in our algorithm? The answer is that we should not only select the assignment with the best score, but also avoid those loops. For instance, for this toy example, we can enumerate all of the options without loops, and here are the 3. We sum up all of the scores and select the best one. In this case, it's in the middle, option 2. The only problem is how do we formulate this procedure? One way to do it is called ILP, which is short for integer linear programming. Here is an example ILP formulation for temporal relation extraction, but note the method is very general. Here we have 2 types of variables. Boolean variable I, indicating the relation between event I and event j. I'm using a 2-label example, just one from left to right or from right to left, to indicate what I means. And another type of variable, a real variable, it's f. It represents the confidence scores for each relation. If we sum them up and then we enforce the no loop constraint by the following expressions, and that's our mathematical formulation for this problem. And overall, we can see again that we are maximizing the score of an entire graph while enforcing transitive constraints. The key step here is how do we understand this expression? Recall I is a binary variable. So if both I are 1 and I are 2 is equal to 1, which means those Boolean variables are true, then I are 3 must be 1 due to this constraint. Otherwise, I are 3 is not constrained at all. So you can see this is how we constrain all of the relations among all of these events. To get all of these constraints, we have to draw a lot of diagrams. And finally, in this paper, we summarized that here is all types of constraints. Here, R1 means the relation between event 1 and event 2. R2 is a relation between event 2 and event 3. And that final column is the constraint that R1 and R2 has enforced to the relation between event 1 and event 3. And on the right, these are the legend for all of these abbreviations. So you may see from the previous table that we have a problem. What if R3, instead of having a unique choice, but instead R3 has multiple choices? Then a small extension is actually very easy. So we just change the previous expression by having this summation score. And one may also ask, what if we want to enforce constraints across different relation types? For instance, what if we want to enforce the relationship between temporal and causal? This slide is explaining how to extend to that scenario. It turns out to be straightforward, and we have highlighted the changes in purple. We can just add an extra term to our graph scoring function and add this extra constraint, making sure that whenever event I is the cause of event j, then event I must be before j as well. To drive this idea home, a recent work at EMNLP 2020 takes 3 types of event-event relationships in one framework, namely temporal, parent-child, and coreference. Recall that the same events, which are captured by event coreference, share the same relationship to other events. And parent event temporally contains the child event. The constraint table here is a little bit more complicated than the one we saw earlier. But again, alpha means the relation between 1 and 2. Beta means the relation between event 2 and event 3. And the main body of the table means the choices left for the relation between event 1 and event 3. And we can enforce these constraints in a global inference. Here in this table, PC means parent-child, AF means after, and this negation sign means after cannot be valid in this new constraint. Please refer to the table for the legend, which I'm not explaining here. So far, we have assumed that a model is already given to us, and all we cared about was how to do a global inference. The next question is, how do we get this model? How do we train it? Some prior works had been via local learning. Local learning means during learning, we don't care about the structure. We just decompose the entire graph into individual edges and feed them to the learning algorithm one by one. The algorithm can be any algorithm, including neural nets, but it's still local learning. Our argument is local learning is not sufficient. In the previous example, imagine a learning algorithm is looking at this pair, ripping and ordered. Even for humans, when we only look at the local context, we don't know the relation between ripping and ordered. We don't know whether it's ordered first and then rip the houses off the ground, or it's rip the house off the ground and then order the evacuation. But now, imagine we are a machine learning algorithm. Annotation says the label is before. So the algorithm will simply update the local model to fit it, which leads to overfitting. However, if we bring in a third event, cascaded, and since we know event ripping is included in cascaded, and cascaded is before ordered, we immediately know that ripping is before ordered as well. So we don't really need to rely on the local model itself to overfit this decision. That's why global information is needed in this task. Again, the question is, how do we formulate it? And the answer to this question is generally termed as structured learning. This is a standard structured learning algorithm using perceptron to do a side-by-side comparison. The left is a standard perceptron, and the right is a structured perceptron. In local learning, an instance is a single pair of events, while in global learning, an instance is the entire situation, usually a paragraph, a document, or even multiple documents. Local learning is unaware of the decision in other pairs, while global learning is using a global inference in between, so it's aware of the entire graph. Note the idea that we can embed a global inference step into the learning iterations to form a structured learning paradigm is very general. Here, another way to enforce the structures in learning, but in a softer way, is used in the same paper in EMNLP 2020, where they softened the constraints and added them into the loss function to minimize it. This is obviously also a clever way to do structured learning. Finally, this is a summary of the progress in temporal relation extraction over the recent 3 years. The setup is that events are given. We can see the previous SOTA was in the high 40s, and with structured learning, probabilistic prior, and new linguistic formalism, the performance got into the high 60s. And then, with the help of neural nets, with the help of BERT and Siamese network, and finally, with this new EMLP 2020 paper using constrained learning, we have seen a state-of-the-art performance now in the high 70s. Using the languages in this talk, the improvements are coming from considering multiple events, multiple relation types, and better representations. There is another thing we're going to discuss next, new linguistic formalism, which is about event properties and definitions. We have said multiple times in this talk that time is one-dimensional physically. But according to this paper to my paper in 2018, we are arguing that multiple time axes may exist in natural language. For instance, police try to eliminate the pro-independence army and restore order. At least 51 people were killed in clashes between police and citizens in the troubled region. This new linguistic formalism, termed as mattress, this new dataset is trying to argue that multiple axes exist. For instance, police tried and 51 people got killed are on the main axis, while to eliminate army and to restore order are on the intention axis. The proposal in this paper was based on the fact that typically these pairs of events on the same axis are very well defined. And in contrast, cross-axis event pairs often lead to ill-defined relationships that are very hard to annotate. Please refer to that table for more details. But let's come back to our previous example. Shouldn't the cause be before the effect? If we apply the formalism of matters here, we will see that give presentations is actually on the intention axis. So it actually doesn't conflict with physics on the main axis at all. Another example was walk versus dinner. If we draw the timeline, we would see the relationships are different in two sentences. This phenomena isn't very popular in practice, so far there is no linguistic formalisms capturing them. But in a recent dataset we have collected, we show that these phenomena are easily distinguished if we use the QA format or question answering format. This new dataset is called TORC, published in EMNLP 2020. Interested readers can refer to my talk for that paper. But here I would like to show that if we further pre-train Roberta on TORC, we can get new state-of-the-art result on the mattress dataset. Finally, here's our summary for today. We've talked about the importance of the relation between events for story understanding. And this task is difficult because each type of relation forms a complex structure, and different types of relations also influences each other. And finally, event formalisms are naturally difficult to define. A keyword in existing works is joint. By finding event structures first, and then enforcing these constraints in inference and or in learning, explicitly or implicitly. But finally, the more important problem often lies in how should we define these relations, or more fundamentally, what is an event, which is covered in other parts of today's tutorial. Finally, this is the references for today's talk for my part, and thanks for your attention. Please stay tuned for our next part of this tutorial.
Hi, this is Muhao Chen from University of Southern California. So thanks for listening to our tutorial. I'm presenting the third technical part of our tutorial. And the title of this part is Understanding Event Processes in Natural Language. So in this section of tutorial, we'll focus on machine understanding of event processes. This part concerns several key challenges of how do we model and support the machine to predict the evolution of events, and how do we support the machine to infer the intentions and the central goal that leads the evolution of events, and how this kind of knowledge about event evolution can help tasks of human language understanding and also computer vision. So the first message I want to bring out is that human language always involves the communication of events. So let's say when we talk about earning a PhD degree, there are lots of events we can talk about. For example, fulfilling the course requirements, passing the qualification exams, so on and so forth, until defending the dissertation. Right? So in previous sections, I think Manling and Qiang have introduced how event-centric information extraction can help automatically recognizing and typing events, inducing the relations between two events, and also identifying the equivalence of events. However, to understand events in natural language, extraction only is not enough. This is due to that events are often not simple standalone predicates. They actually evolve and form processes such that in terms of earning a PhD, we know that after fulfilling the course requirements, it's typically followed by passing the qualification exams and also doing dissertation proposal. And the events are often described in different granularities, such that a more coarse-grained event, such as publishing a paper, it always involves a more fine-grained event process of writing the paper, passing peer review, and also presenting at the conference. And events are often directed by specific intentions or central goals, such that we know that all the events at here, they are directed by the same central goal of earning a PhD degree. So all those kind of properties, they are often not directly extractable from text, so such that they are often going to involve lots of efforts of predictions and reasoning. So in this part of the talk, we will focus on event processes, such that each of which is modeled as a set of partially ordered events that are centered around a common protagonist. For example, the process of earning a PhD requires the protagonist, which is the student, to fulfill the course requirement, pass the qualification exam, so on and so forth, until the student files the dissertation and maybe gets approved. And there are various fundamental prediction problems about event processes, such that we would expect the machine to perform event process completion. That is to say, given a partially complete process, the machine should understand what should happen next. Right, and there are also the problem of intention prediction, such that what is the central goal of, let's say, digging a hole, putting some seeds into the hole and fulfilling the hole with the soil. The central goal is planting a plant. Right? And also, there's this fundamental problem of doing membership predictions, such that does the machine understand what should be the necessary steps of buying a car? And in the same context, there's also salience prediction, such that does the machine understand that in terms of earning a PhD, defending the dissertation is much more important than doing an internship. So besides those fundamental prediction tasks, understanding event processes are often important to real-world NLU tasks. For example, let's take this example from narrative prediction. Suppose that we want the system to complete the partially complete story about one day Wesley's aunt came over to visit. He was happy to see her because he liked to play with her. Then when she started to give his little sister attention, he got jealous and then he got angry at his auntie and bite his sister's hand when she was not looking. One way to infer the more plausible continuation of the story is to keep track of the evolution of events in the story, such that we all know being jealous, getting angry, and biting someone is more likely to be followed by getting scolded rather than getting a cookie as a reward. So similarly, when we perform machine comprehension tasks, we may often see cases where understanding a piece of text from, let's say, a biology article. This is also centered around understanding a biological process, where light absorbed is leading to water is split, which is further led by transfer of the electron and the hydrogen ions. So in this context, understanding the biological process is important to answer the question, what can the splitting of water leads to? So I'll split the rest technical content into 4 parts, for which I will first focus on recent advances in solving the problem of event process completion and also event intention prediction, followed by how event processes are applied to different downstream natural language understanding tasks. And in the end, I will also discuss a little bit about open research directions in the context of event process understanding. So first, let's look at the event process completion task. So there are actually two different definitions of event process completion. One is that given a partially complete event process, a system tries to predict the missing step, or most of the time predicting the possible future steps. And the other problem definition is that given a coarse-grained event as an objective, the system tries to predict the entire process from scratch. So one of the earliest attempts to automatically complete the event process, which follows the aforementioned first problem definition, is published by Chambers and Jorovsky in 2018. In 2008. So this pioneering work seeks to conduct unsupervised event process completion based on corpus statistics. The principle is that given a very large corpus, in this work, the authors used 11 years of gigaword corpus, and their system captures the co-occurrence of events in the same local context based on their PMI. Then during the inference, given a partially complete process, the next event will be predicted as the one which maximizes the accumulated PMI. So here we have an example of prediction given by their system, which shows that given the events about pleaded, admitted, and convicted, the next event is likely to be sentenced, paroled, or fired. And in the same work, the authors also show that the event process completion leads to as much as 36% of improvement on the New York Times narrative clause test over the best baseline during that time. There are also several significant works that follow Chambers and Jorovsky's design. One of them is by Radinsky and Horvitz in 2013. So this work extends unsupervised learning of event chains to cross-document scenario, such that given, let's say, 6 months of New York Times articles, this system first identifies topically cohesive documents along this period of time. Then from the titles of those topically cohesive documents, a maximum cross-entropy-based model captures the co-occurrence of events in a chain, which has a similar effect to the previous PMI-based model. And this technology is applied to predict possible forthcoming news along the time, such that it can predict the likelihood of cholera rising to be high after the drought followed by the storms in Angola. This is actually also a successful application to an automated timeline generation. So the aforementioned line of research focuses on predicting forthcoming events after a partially completed event process. Then a more challenging research question would be, can we induce a new process without seeing a part of it? Say, given the objective of buying a house, can we let the machine automatically induce all of these steps without knowing a part of it? This is actually a hard problem that is recently being attempted by our EMLP 2020 paper. So the general idea is actually very straightforward. So basically, we try to leverage the analogous property of events and transfer the knowledge about some processes that we have already known to some new processes. So actually, it also mimics how human understands event processes when we try to predict something that we are not familiar about. For example, assume one has never bought a house, therefore may not know the detailed process of it. But we might already have ideas about other relevant processes, such as how to buy a car or how to rent a house. And intuitively, these relevant processes should contain some relevant steps. Based on such relevance, we may guess the necessary steps of buying a house, even though we do not have the real experience. So this is the overall framework of our system. So in the first step, based on the assumption that the process objectives sharing the same predicate or argument are analogous to each other, we would first decompose the objective of an ensuing process into two dimensions, the predicate and also the argument. For example, given the objective of buying a car, we'll decompose it into buy, which is the predicate, and also the objective house. Then for each of them, we will find a group of relevant reference processes that may share either the predicate or share the same argument with the objective. For example, given this objective, we will get lots of reference objectives of buying something or about some action that is taken upon a house. Then given lots of those reference processes, the system will try to predict the event process of the objective based on the content in those retrieved reference processes. And to do so, the second step, which performs the event conceptualization, it acquires a probabilistic object representation for each of those reference processes. And in the end, the abstract representation will be merged into a common pattern, which will be applied within the event instantiation module to get the final prediction. So I'm actually not going to go into more details of each part of the modules, but here are some interesting experimental results based on event processes extracted from WikiHow. So from which we can tell that the proposed system can largely outperform large sequence-to-sequence generation methods and achieves about half of the human prediction. And on the right-hand side, we show that some case study indicates that, let's say, given the objective of treating the pain, the system can predict some meaningful processes like identifying symptoms, seeing doctor, recognizing the symptom, and then taking some supplements, which are actually quite meaningful. So this is noteworthy that this kind of generating new event processes is a quite challenging open problem, and there is still much gap to fulfill between the machine performance and the human performance. The interested audience can are welcome to play with the released dataset that is available on the CoreComp website. So next, let's talk about event intention prediction problem. So the motivation of this prediction problem is that people can easily anticipate the intentions and the possible reactions of participants in an event. For example, given the event, person X cooks a Thanksgiving dinner, it's likely that the person X's intention is to impress their family, and the reaction may be the person will get tired and the family will be impressed. Okay. So for this kind of reason, we would also expect a common sense aware system to perform such prediction, which is first attempted by the Event-to-Mind paper published in ACL 2018. So the Event-to-Mind system is developed based on a large crowdsourced corpus, which contains around 25,000 events and also free-form description of their intentions and reactions. And the model is trained on a large corpus to perform a sequence to n-gram generation, which actually shows pretty good generalization to give free-form intention prediction. For example, given the event, person X cooks steak, it is able to give some meaningful intention prediction, such as to kill their hunger, to make dinner for the family, to eat steaks, and so forth, and also meaningful prediction for reactions and other people's reaction. So actually, this Event-to-Mind work later leads to well-known tasks of and also systems about common sense reasoning, including atomic and comet. Those will be later covered by Homing in his part of section, so I'm not going into details of those works in my talk. But on the other hand, I want to say that this kind of intention prediction naturally also applies to event processes rather than just single events. So this is actually suggested by cognitive studies such that a process of events is always defined by the central goal and the intention behind the process. For example, when we see this process of digging a hole, putting seeds in the hole, fulfilling the hole with soil, and water the soil, people are easily able to tell that this is a process led by the central goal of planting a plant. And similarly, when we see the process of making a dough, adding toppings, preheating the oven, and baking the dough, it is likely to be the process of cooking pizza. So actually, humans can always understand event process by hypothesizing the objectives those co-occurring events aim for, or the ultimate sequence the process seeks to accomplish. So naturally, we would also require a common sense-aware intelligent system to perform this kind of inference. So in this 2020 paper of ours, we propose a new cognitively motivated semantic typing task of event processes, which aim to infer the overall action the process seeks to take, and also the type of objects the process should affect. So to facilitate the research on this problem, we also contribute with a large data set of typed event processes, as well as an effective hybrid learning framework to address this problem based on indirect supervision. So the dataset we extract is from WikiHow, which is a large community website containing professionally edited guideline articles. So this dataset comes with more than 60,000 event processes, each of which comes with free-form labels of action and object types. It is noteworthy that the dataset poses a non-trivial learning problem. Specifically, here we have a very diverse type system, such that it has over 1,000 action types and over 10,000 object types. And over 85 of the labels appear less than 10 times, among which nearly a half of those are actually one-shot. Also, in around 90% of the processes, the labels do not appear in the content of the event process itself, which means that an extractive method to address this task will easily fall short. So to solve this non-trivial typing problem, we propose a practical form of indirect supervision based on gloss knowledge. That is to say, instead of directly predicting the type labels based on the event process content, we actually find it to be much more plausible to predict the correct WordNet gloss that defines the type labels. This is due to that the sense definition in the gloss provides much richer information than the label itself. Therefore, it is much easier to seize on the association between a process gloss pair. And also, we find that the gloss provides set information that jumpstart future label representations that are rarely seen or even unseen in training. So this is the overall architecture of the proposed P2GT framework. So in training, we use a Roberta language model to encode the sequence of events in a process. And we also use the same language model to encode the gloss of the label. And to select the correct gloss for a polysemous label, we also incorporate a pre-trained word sense disambiguation model. And the learning objective conducts learning to rank for both the action type and also the object type accesses. And the inference phase will predict the top ranked glosses out of all labels in the corresponding type axis. So the results here show the promising performance by the proposed system, such that it leads to 3.4 to 4-folds of mean reciprocal rank over the Roberta-based sequence-to-sequence generator, which is actually an improved version of the previous event-to-mind system. Specifically, we do see that the indirect supervision from gloss knowledge brings along the most improvement, such that the 2.9 and 3.3 folds of MRR is led by the indirect supervision with gloss knowledge. And we also see that the joint training also leads to notable improvements, indicating that the effectiveness of leveraging complementary supervision signals. Although we do see that the sense selection technique based on WSD does not necessarily lead to much improvement, since the predominant senses are often representative enough to jumpstart the representation of a label. So here we also provide a case study which shows how the system performs process typing on news domains. For example, we do see that the P2GT system is able to understand that making explosive material, obtaining sharp nail, and obtaining a container, and also installing a trigger. This is likely to be a process of assembling a grenade or assembling a blaster, even though that it is clearly this kind of process does not exist in WikiHow. So in this table, we also mark all field short labels with less than 10 appearance time in the dataset as blue, which indicates that leveraging Glow's knowledge actually helps the system to make fair prediction. So there is also a web demo of the system, which can be found on the European Core website through this URL. Next, I will give some introduction about downstream tasks that are essentially supported by event process understanding. So since event process models the plausible evolution of events in the context, they can be naturally used to improve the consistency of narrative prediction. So a narrative prediction task often requires a system to predict the possible continuation given a piece of narration. For example, here there's an instance from Rock Story narrative close test. So between the two optional endings, he was scolded and she gave him a cookie for being so nice. Obviously, the first ending is more plausible to continue the story about the boy did something wrong. Right? And to address this task, the Snake Labs work published in 2017 trained a language model that captures 3 types of sequential features, which includes event sequences extracted from New York Times data, and also the sentiment trajectories and also sentence topics in those stories. And as expected, the experimentation shows that the event sequences is actually the most important factor among those 3, such that using the sequence, the event sequence only, is already able to perform very good performance. So similarly, modeling event processes is also important for machine reading comprehension. So in this task, a system is required to answer some questions that are relevant to a given article. This example is from this award-winning paper in EMLP 2014. So here, to understand the biological process described by the scientific literature, the proposed method also extracts events and event-event relations in a biological process. And the question answering is conducted as matching the events in the question and the candidate answers with the extracted event processes, such that in this paper, the authors also show that the knowledge about event evolution is also very important to this kind of scientific machine comprehension. So another key application is video segmentation. So this task aims at understanding the content of a video and split it into different relatively independent segments. For example, let's say given a video of making a pancake, this can be split into segments about maybe background and also different steps of cooking. So in several recent works by Zhukov and Fried, this task is performed by first extracting the narration in a video, then aligning the narration to different steps of event process extracted from WikiHow. So in this way, different steps in the event process naturally serves as an anchor for different video segmentation. So in the same area, there are also works directly focusing on recognizing and modeling event processes in video. For example, in the most recent work by people from Columbia University, they proposed to use hyperbolic embeddings to capture event evolution in videos. Here, because the same kind of event process may branch into different possible paths of evolution, it naturally forms hierarchies that are suitable for being captured by hyperbolic geometry. So this is actually a very new work that has just been announced last month on arXiv. So lastly, I will provide 3 pages of slides about a few open research directions related to event process understanding. So here, the first problem is salience detection in event processes. So previously, we have already introduced the problem of intention prediction for event processes. But at the same time, another unresolved problem is that the events in the same process are actually not equally important. For example, let's again take this process of planting a plant as an example. We know that among those sub-events, digging a hole, putting seeds in, filling the hole with soil, and watering the soil, clearly that even if we remove the event of watering the soil, we can still tell that this is a process of planting a plant, right? But if we remove the sub-event of putting seeds in the hole, just by giving the process digging a hole, filling the hole with soil, and watering the soil, it is not likely that what kind of central goal is actually behind the process. Maybe it's burying something, or maybe it's planting something, but we are not even able to tell what kind of object we are trying to bury or planting, right? And in the same context, in terms of the process of earning a PhD degree, we know that defining the dissertation is much essential. But doing a TA-ship is probably less important, and also doing an internship is optional. So here the question would be, is there a way to automatically identify salient events in a process? And furthermore, would this kind of salience knowledge help downstream tasks such as objective summarization? This is one interesting open direction that has not been resolved yet. And the second problem is reasoning about ordering of events. So considering that the events in a process may not be necessarily described by a document in the same order, then how do we identify the correct ordering of the member events in a process given each document is an unresolved challenge. So here the problem, for the problem, I want to mention 2 notable benchmarks that are both published in the past in MLP. One is the crowdsourcing-based dataset Torque, which is actually by Chang. The other is extracted from WikiHow, which is by Chris Callis and Birch's group. So there are more tasks that could benefit from understanding event processes. And one is that we have shown that some previous work have already used the event process to improve narrative prediction. So to go one step further, can we actually use the knowledge of event process to improve the consistency of utterance generation or utterance retrieval for chatbots? Is another interesting task. And besides, it is also important to develop reliable learning systems for understanding clinical event processes, such that the machines might help clinicians to perform expensive tasks such as diagnostic prediction or phenotype prediction. So in this direction, I believe transfer learning and structured prediction can be particularly important since they are often lacking learning resources due to privacy issues, and there are also dependencies among phenotypes and disease labels. So those are the key references to the works I have covered. Thank you. Happy to take questions. And please send emails if you have any questions.
Hello everyone, this is Hongming. I'm currently a third-year PhD student at HKST working with Professor Yang-Qiu Song and a visiting PhD student at the Kokang Group working with Professor Dan Ross. In the first section, I will introduce how to understand the common sense from the angle of events and how could we collect those event knowledge. Okay, so let's get started. Common sense is crucial for understanding human language. For example, when we see a sentence like John stepped in a puddle and had to go home to change, to understand this sentence, we need knowledge like step in a puddle can cause shoes get wet, which can cause you to feel uncomfortable, which can motivate you to change. So from these examples, we can see that the common sense is deeply connected with the events. Okay, so in this talk, I will first introduce the connection between event knowledge and the common sense knowledge. Basically, how can we understand the common sense from the angle of events? After that, I will introduce 3 popular methods we typically use to collect those event knowledge, including human annotation, automatic IE systems, and the language modeling. After introducing the instance level event knowledge, I will then talk about how can we go to a more abstract level. Basically, how can we collect those schema level event knowledge? In the end, I will conclude by comparing the advantages and disadvantages of all event knowledge acquisition methods. Okay, so let's start with the common sense. For ordinary people, common sense basically means the good judgment about the world around us. And in the AI community, it is used as a technical term referring to millions of basic facts and understandings processed by most people. One unique property of the common sense is that common sense is about preference over ordinary objects, and they are not inevitably true. So basically, different from factual knowledge, like Obama was the president of the United States, which is always correct, the common sense knowledge is not. For example, if you forget someone's birthday, they may be unhappy with you. But if this person is your friend and he really understands that you are very busy these days, he won't get angry. And from these examples, we can see that the common sense is about preference. So naturally, let's go a little bit deeper and try to think about where could such preference happen. So based on DSGNbzuS1s6x81ZSbSHHV5uGDxJXePeyKy semantic theory, the semantic meaning in our language can be described as a finite set of mental primitives and a finite set of mental combinations. And actually, the primary units could include many things. So the first kind of primary unit are things or entities. For example, cats. We all know what cat is about. It's a kind of animal that are typically very cute and have 4 legs, 2 eyes, 2 ears, 1 tail, etc. Besides that, another important parameter is the state, such as the cat is cute or the cat is smelly. Actually, I think it is fair to say that our understanding about things can be reflected via states, because the semantic about things is really just the union of all possible states that it could appear in. So basically, the states are described in certain properties of the things. Okay, so everything we have discussed so far are static. However, the world is dynamic. So we also need to understand events. Basically, events describes the changing of states. So here is an example, like this cat is running. Actually, from this event, we have many interesting knowledge about it. For example, like why it is running in such a hurry. It may be because like it just sees some delicious food, or it just wakes up and sees some weird guys trying to make a video of it. It just got scared. Consider the knowledge about things can be effectively represented by the states and events, whose overall term is called eventuality. You can see that the common sense is really, or common sense can be reflected with the human preference over eventualities. Okay, so naturally, the next question would be how to represent such preference so that the machines can understand common sense. To answer this question, we need to think about how are this kind of preference is expressed in human language. So based on the lower bound of the semantic theory, if we remove the grammar from the linguistic description, we will get semantics. So basically, understanding language needs both the speaker's knowledge of the language and the knowledge about the word. And here, the knowledge about word includes the common sense we care about. Okay, so here are some examples. There are 3 sentences. Should we take the junior back to the zoo? Should we take the llama back to the zoo? Should we take the bus back to the zoo? Even though these 3 sentences share the same grammar structure, they are describing totally different events, which may have totally different reasons, effect, or like sub-events. So if we provide a little context, like it is so dangerous, which one of them are most likely to happen as the next sentence? I would like to put the second one because lion is a kind of dangerous animal. We all know that. So basically, this example shows that when the grammar is controlled, our selection can be used to reflect our understanding about junior, lion, and the bus, which is exactly the common sense knowledge we are trying to capture here. Historically, people used to call such grammar-based semantics or preference with the term selectional preference or semantic fit in some other literatures. So basically, selectional preference is a kind of relaxation of selectional restrictions and is often used as syntax feature. Originally, it was only applied to the easier hierarchy in WordNet and word-object relations. Actually, the idea of central preference is very simple. We control the grammar like a direct object dependency connection and its head. Basically, the words humans should be able to have preference about the argument it can be connected to. With this formulation, we can easily use the frequency or some possibility score given by different models to reflect human preference. Here are two examples. The cat is more likely to be a kind of animal rather than plant. So if one model or knowledge graph can manage to assign higher score to the first combination rather than the second one, we can claim that this model or KB understands humans' preference about this piece of common sense knowledge. Similarly, if a model managed to assign higher score or weight to the first table, like eat DOBG food, rather than the second one, we can say that it understands the common sense knowledge that we are more likely to eat food rather than rock. Of course, these two kinds of relations are not enough to cover all the common sense. People start to extend the definition of central preference to other dependency relations and subject. So for example, it is more likely for a singer or person to sing rather than the house. Actually, we can further extend it to second order. The motivation is that sometimes humans do not have preference for the subject or object of a specific verb, but they do have preference about the property of the subject of an object. If we further extend, we will get the higher order central preference, which describes the common sense knowledge about complex relation between events or states. Like eating dinner may cause a person to be full rather than hungry. We call it higher order because really the semantic unit here is the eventualities rather than the words. We need to view each eventuality as a whole. So to summarize what we have discussed so far, the common sense can be represented by the higher order central preference over eventualities. To demonstrate that the preference knowledge about eventualities, most of them are defined on linguistic relations, are indeed the common sense we want. This trans-OMCS paper tried to convert a linguistic-based eventuality KG into human-defined common sense knowledge, like consonants. And it turns out that there are many interesting patterns and overlaps between those linguistic relations and the human-defined common sense relations. Okay, so assume that we have this linguistic graph, which contains an event customer is food and the state is full. There is a discourse relation results connecting these two eventualities. And inside those events and states, the words are connected with dependency relations like subject or object. We can find many interesting overlaps between this graph and the common sense assertions in customer. For example, we can find out that the customer actually appears as the subject and the tail as eat food appears as a verb and object. We can then conclude a pattern that for the capable of relation, we can extract the subject as a head and the combination of verb and object as the tail. Similarly, for the receive action relation, we can see that the object usually can be used as the head and the verb is the tail. Last but not least, we can also see some interesting patterns across different events like this one for the causal relation. So after they collect those patterns, they can then apply the patterns back to the original event KG to acquire large scale of common sense knowledge. We borrow some examples and show them here. The confusing phase means that humans think that extracted knowledge might be problematic. But I think the overall quality is quite good. For example, we can actually observe some interesting common sense, such as human is capable of high cells, and love can be caused by being happy and pain. Okay, so after introducing the connection between event knowledge and the common sense, I will then introduce how do we typically acquire those event knowledge, and I will start with the human annotation. So as an important semantic unit, the study on event semantic has long been the focus in the NLP community. Throughout the years, many event-centric resources have been developed, even though they may have different purpose and scale. For example, FrameNet is considered to be one of the earliest knowledge base defining events and their relations. It provides annotations about relations among about 1,000 human-defined eventuality frames, which contains 27,000 eventualities. However, given the fine-grained definition of frames, the scale of this annotation is limited. After that, ACE reduced the number of event types and annotation more examples for each of the types to make it more dense. Different from the pro-bank and no-bank builds frame over syntactic parse trees and only focus on annotating popular verbs and nouns. Okay, so all aforementioned resources are mostly focusing on the event themselves and do not care too much about the relations between them. But there are some other resources do care about the relations. And an example is this TempBank. It cares about the temporal relation between different events. Recently, with the development of those crowdsourcing platforms, crowdsourcing actually kind of replace expert annotation, becomes the more popular way to construct the event KVs. And a popular example is the ConceptNet. Even though its original design purpose is the common sense rather than just events, it does contain 4 event relevant relations like has sub-event or has prerequisite, etc. Besides the ConceptNet, several other popular crowdsourcing event bases are Event2Man, Propora, Atomic, and Atomic 2020. They often focus on specific relations between events. For example, Propora focuses on the scientific process, while Atomic focuses on the 9 human-defined relations between daily events. Okay, so as a quick conclusion, the most significant advantage of those event-centric knowledge base is that they are often of high quality, but at the same time, it may suffer from the expensive cost, the small scale, also the limited relation types, because they always need to first define the relation we care about, and then we can annotate them. Okay, so after introducing the previous human-crafted event knowledge resources, I will then introduce how do we acquire the event knowledge automatically with information extraction techniques. So the first work I want to introduce is Nollywood. As one of the earliest, largest event knowledge graph, it extracts event knowledge from movie scripts. Specifically, it defines each event to be the combination of a verb and its object. Even though it calls it activities, but I think the meaning is the same. And it only focuses on the temporal relation between events and use 560 movie scripts. So here is the overall pipeline. It first leverages existing tools like cross-parsing and word synthesis to parse the raw corpus. After that, based on the parsing results, they build a graph inference model to align all the extracted event knowledge together. So the main purpose of this step is to minimize the influence of the conflict. And then in the last step, it built the event taxonomy based on the clean knowledge and generate the final KP. So here is a case study showing the extraction results. From the scene, we can actually extract some interesting event knowledge that we first knock the door and then open up the entrance, and then we can enter the office. A big advantage of this approach, of course, is the quantity. So as this approach is automatic, it is much cheaper than the crowdsourcing. It can effectively extract the knowledge about 964,000 events, which is much larger than ConceptNet. Yeah, as you can see here. Besides Nollywood, another large-scale event-centric knowledge graph is Acer. Compared with Nollywood, the overall structure of Acer is more complex. As a result, it has the potential to cover richer event knowledge, but also faces larger extraction difficulty. Specifically, Acer is a hybrid graph, and each node in Acer represents the eventuality, which is in the format of dependency graphs. Currently, Acer uses all the discourse relation between eventualities as the edges. As for the resource, it uses 11 billion token corpus as the raw data, basically including Yelp, MIT, Wikipedia, Reddit, subtitles, and electronic books. Okay, so here is the overall extraction pipeline. After collecting the raw corpus, Acer first pre-process the text with the dependency parser and then perform the dependency-based eventuality extraction algorithm, as you can see here. After that, Acer will extract discourse relations from those candidate instances. Considering that compared with eventualities, the discourse markers, especially the good ones, are very rare. So it also introduced an additional bootstrapping framework to improve the overall coverage. As for the results, we got Acer. As you can see from this example, Acer is essentially a hybrid graph. Like each node in Acer is a hyper edge of words that describes an eventuality, and there exists a heterogeneous edges among eventualities. So the current Acer contains 194 million eventualities and 64 million edges. Actually, lots of interesting common sense knowledge can be found in this graph. For example, the eventuality I eat food appears about 3,000 times in the whole KG, while the eventuality I eat rock never appears. By comparing these two, we can actually see that the statistics about eventualities actually reflects lower order cycle preference, like we are more likely to eat food rather than rock. Besides that, we can also observe some interesting higher order cycle preference here, like we often make a call before we depart away, and being paired and being hungry also happen together. As for the quantity and the quality of the eventuality extraction, the overall precision is about 80%, which is pretty good, especially considering that they do not use any annotations. An important reason for that is that the eventuality extraction algorithm is actually quite strict. They kind of sacrifice the recall to make sure the precision. As for the scale, of course, scale is also an important issue here, but since the approach is unsupervised and they can easily scan more data, for example, as you can see here, it's got about 1 million to 100 million unique inequalities for each of the selected patterns. As for the edges, it's got 64 million edges in total, and here are the distribution and the quality of all the patterns, all the relations. And as you can see from this example, in general, the distribution is not very balanced. Some of the relations appears over 8 million times, while others only appear less than 6,000 times. As for the quality, it is a little bit worse than the eventuality because the higher order cycle preference knowledge is more complex. So here is the set comparison of all the aforementioned event-centric KBs we have built. So currently Acer is the largest one because it is automatically extracted from unlabeled corpus. It's pretty cheap. By scanning a large scale corpus, it is 100 times larger than Nollywood and 1,000 times larger than Concept. Okay, so in the last part of the instance level event knowledge acquisition, I will introduce how to leverage language modeling to acquire rich knowledge about events. So recently, the most important breakthrough in the NLP community is the pre-trained language models. Well, with the help of deep models and the large-scale pre-training corpus, the language model actually managed to memorize rich knowledge, and common sense knowledge is not an exception. So basically, a natural question would be, how can we mine such knowledge out of those language models? And to answer this question, Comet proposed a supervised solution. By learning with a state common sense knowledge graph, basically concept net or atomic, it managed to produce interesting common sense or event knowledge with the help of these pre-trained language models. And here is the overall framework. Even though the approach is quite straightforward, it first encodes the head and relation with an encoder and try to predict the tail event with a standard decoder. The overall result is quite impressive. Besides extracting event knowledge from the language models, as those language models may also not be perfect, people also care about how can we help them to better understand and memorize event knowledge from raw corpus. And the Taco LM is a good example. Specifically, it aims at helping language models to understand how long each event typically lasts for. Some examples are like moving chairs will typically last for seconds, but moving piano will last for hours because piano is much heavier. And similarly, moving to a different city may take longer time. With the goal of building a general time-aware language model with minimum supervision, this language model starts with a focused and supervised information extraction step, in which they use a set of high-precision patterns to acquire temporal information. This actually helps the model to overcome reporting bias, as we can automatically extract those knowledge from the natural language, natural text. And then in the second step, they can propose a joint training for the language models to help the model understand both the original semantics as well as the temporal information about events. One thing worth mentioning here is that we actually consider multiple temporal dimensions. This is beneficial. For example, we may not see direct mentions of the duration of brushing teeth. However, we know that it is shorter than a morning, as the frequency is likely to be every morning. So this provides further generalization ability to combat the reporting bias. Finally, they can obtain the final model, Taco LM, basically a BERT transformer that is more aware of time. Okay, so here are some technical details. So in the information extraction step, a set of high-precision patterns based on SRL parsing results are used to mine those temporal information, including duration, frequency, and typical time. Considering we have a raw sentence, I played basketball for 2 hours as an example, so they can first apply as an SRL model and get the verb and argument. In that case, there is a temporal argument for 2 hours, which can match the pattern they designed for the duration. That is, we know that this 2 hour is describing the duration of this verb played. Following this, they can then transform the original sentence into a training instance of event. It basically includes the duration as well as the values, also this event, of course. In total, they got 4.3 million such tuples for the pre-training. And for the model part, they employ a simple objective of masking some tokens in the formatted sequence and then recover them such that the model can know about time. With higher probability, they will mask the temporal value while keeping the others. Otherwise, they will instead mask some event tokens and keep the temporal value token unchanged. So in this case, they can actually maximize the conditional probability of the events and the value at the same time to preserve the original capability of the language model. Okay, so after introducing the common way of collecting instance level event knowledge, I will then introduce a recent work that focuses on schema level event knowledge. The good thing about schema level event knowledge is that it can help us to achieve a kind of abstraction to transform the knowledge from observed event instance to unseen ones. At the same time, it can also help select the salient event knowledge and minimize the influence of noise. Here is an example. Assume that we have 2 instance level event graph. Okay, so even though they are not describing the identical events, some components are actually shared. For example, how are these transport events are connected with the attack event? These events are the same. So to effectively find such schema knowledge, we can first generate a set of passes by random walk over this graph or those instance graphs, and then we can learn a path language model to modeling the concurrence information of all of these nodes. And then as a result, we can get this final graph schema. So here is how they train the path language model. The approach is actually very straightforward. You can concatenate multiple passes together and then treat it as a natural language sentence and feed it to the model and to model the coherence of those passes. One thing worth mentioning is that to capture the co-occurrence information of 2 passes, they also introduce an additional neighbor path classification loss to help the model to know such kind of knowledge. After we get those schema graphs, we can then apply them back to recover the instance graph. For example, if we only see an incomplete instance graph G, we can actually leverage the schema graph we got here, basically S, to help us to predict the missing nodes or edge in the graph so that we can combine them together to basically we can understand something has not been explicitly stated out in the document we have. Another application of the schema is that we can use it to help improve the aforementioned event extraction system. For example, if we already extract an event, we know that it belongs to a schema. We can pay more attention to other events in that schema. It is a little bit kind of, we already know what we are trying to look for here. As for the results, they tried combining this schema knowledge with one of the state-of-the-art model, 190 system. And it turns out that, yeah, it can help it to extract both the event triggers, also the event arguments, as well as the relations between those events. Okay, so here is the quick conclusion of the 4th section. So in the first part of this talk, I demonstrated that there is a transferability from event knowledge to common sense knowledge. And after that, I introduced those popular existing event knowledge acquisition approaches to show that actually compared with the common sense, which can only be annotated or acquired by human annotation, acquiring event knowledge is much cheaper and more scalable. And last but not least, we introduced the advantage and disadvantages of all of these event knowledge extraction pipelines. We can see that none of them is perfect. They all have some advantages or disadvantages. For example, in terms of the quality, of course, human annotation is the best one, but it may also face the scale problem. On the other hand, automatic event extraction systems and language models do not have a scale problem. Also, language models tends to have the highest relation coverage, but it may not have a very good explainability. So also, as well as the robustness, because it may overfit too much to the training data. So in terms of the downstream tasks, so based on our current experience, language model is still the easiest one. So that is all for the full section. Thank you so much for your time. And here are all the key references. Thank you so much. Thanks.
Hi, everyone. So now you have heard all these exciting methods from the previous sessions. Now, Dan and I will continue to talk about applications, some of the mini challenges, and some future directions that we would like to recommend for the next 5 years or 10 years. We'll go over some applications in different domains, and then we'll be talking about some of the mini challenges for each component that we have seen in the previous sessions. The first application, as we mentioned in the introduction, is about writing history book. So can we help historians and librarians to write more complete and authentic history books? Because the human written ones are often incomplete and highly biased, depends on who is writing the book. This is especially important for the current era of information pollution, because there's just simply too much misinformation and disinformation going on. For example, Bill Gates was falsely accused as the creator of coronavirus just because he gave a TED talk 5 years ago and he donated a lot of money. So why humans tend to think of this kind of a ridiculous rumor as true information? Because the human is really good at connecting dots. So what we would like to do is to putting together a very comprehensive event knowledge base that will show the connections among events and how they evolve over time and how they are connected on the spatial dimension and who are being shared, who are the major characters, and then also generate an authentic summary. So this will look like a timeline, but also looks like a Wikipedia page, so that we can keep updating it automatically, and a human can do some curation on top of it. We can arrange the events in different dimensions. We can, for example, use news timeline. In each chapter, you will see an episode title, and under each chapter, you will see a sequence of temporally ordered events. For example, this shows 2019 Hong Kong protest. There are different episodes that have different characteristics, and then each chapter, you will see how their different events are connected to each other. We can also order events in a hierarchical way. For example, all this deep hierarchy shows ISIS attack activities. The second application is we can apply the whole framework to fully understand news and also recommend written news. And this is an example from our last year's ACL demo. We can also use this framework for better question answering, especially when the question involves multi-hop events. For example, we can ask questions like, will primary schools in Europe admit non-vaccinated children around September 2019? So here there are two events. One is admission, the other is vaccination, and we need to see who are being, what are the arguments that are being shared by these two events. Similarly, we can use event injection, event tracking, and reasoning in dialogue system. For example, this chatbot can talk to the user about what happened in the road trip and then help the user to solve the problem. We can also apply event understanding techniques to monitor disasters and try to allocate resource better. So this is a screenshot coming from the system that we developed for showing event heat map. We can show to any English user what's happening from the world by looking at what is the information need associated with what entities from 300 languages. And we can also apply that to intelligence analysis to help intelligence analysis. For example, for MH17 crash from the event knowledge graph, we can clearly see there's a purple graph and a blue graph. They are talking about two different hypotheses. One says pro-Russia rebels in Ukraine is attacker. The other one says Ukrainian government is attacker. So a user analyst can come in to show their background knowledge and then pick one of these two hypotheses. We can also show the association between these events and the subtle implicit attributes such as moral value so that we can understand the causality. Of course, a much better way to use this kind of technique, or much more useful one, is to accelerate scientific discovery. So we can use this kind of technique for social good. So how should we do this? We can mine millions of scientific literature for a particular domain, for example, for molecular synthesis, and then we can construct multimedia knowledge base, and scientists can interact with this kind of knowledge base using queries, and they can also see very comprehensive summary from the knowledge graph. So here's one example that we adapted the system we showed in the first session to a COVID-19 domain. The only difference is that in the encoding part, in addition to the contextualized embedding, we should also take advantage of domain knowledge. For example, we can link the mentions to external ontologies and use the hierarchy and definition properties in the ontology to enrich the representation. And then in the meanwhile, we should also take advantage of the special features of the images in this kind of scientific literature. For example, in molecular synthesis, you usually can further pass the pictures using graph passing so that you can see how the different components in this molecule are interacting with other components in other molecules. And then we can use this multimedia representation as we already showed in the news domain, and then discover multimedia knowledge graphs that will look like this. And then use this, we can then ask questions that usually required for a geography person report. For example, here, the question is about individual data. So we not only show the evidence sentence, but also the corresponding subfigures that are associated in the same subgraph. And sometimes when the answer comes from many different papers, we can show there's a path or subgraphs connecting, for example, the drug and the symptoms of side effects symptoms, so that scientists don't have to go back to read many papers. They can just check this subgraph, and then if they want to check details, they can check the evidence sentences and subfigures. So these are all super exciting. But we all know that there are many remaining challenges, and our components are far from perfect. So the major challenges for event injection is that we are still lacking of scene understanding, global knowledge acquisition. So for example, here in this paragraph, the trigger of this event die appeared at the end of the paragraph, but the time 1985 is far away from this trigger. So a sequence labeling system usually miss the argument like the time, because of the complicated structure and because of the unusual way to narrate the events. But if we look at the hierarchical relations, we know that in this situation, the transfer ownership, the capture event and the die event happen on the same boat. So they should also share the same time argument. So in computer vision, they actually have really nice top-down reasoning. Usually people will do situational recognition first, identify the scenario, and use the scenario knowledge to guide event injection. So we probably should follow a similar idea to improve event injection in the future, especially when the triggers and arguments appear in the long tail. For example, these are some rare triggers and arguments. They never appear in training data, so our baseline framework will fail to identify all of them. And also when some triggers, especially supportive verbs, they are highly ambiguous. So it depends on the situation. It's really difficult to just use the trigger word embedding to detect the event types. For event coreference resolution, the major challenge now is to distinguish coreference and partial coreference, or distinguish coreference from super event, sub-event hierarchical relation. For example, in the first example, shooting and fire, they are just in a hierarchical relation rather than coreference. And in the second example, these two events are a sequence of sub-events that belong to one parent event, but our framework mistakenly identify they are co-referential because they share similar local content. For visual event injection, as we have already seen, we still need to develop more advanced and higher quality pre-processing tools, for example, localization. So these are some examples that show when the bounding box is really complicated or very small, including a lot of instances, then there are localization or grounding always fails. So this will affect the quality of the multimedia embedding representation and the cross-media transfer. So what should we do? The first direction we should focus on is to do knowledge acquisition and use symbolic knowledge to do some reasoning. For example, we can take advantage of Wikipedia to discover some spatial patterns and temporal patterns so that we can use that to enrich our event representation. We can also learn some knowledge, for example, like duration from Google Ngrams. And we can also look into the layout and how the events are co-occur in the same article or through the Wikipedia links, or we can look at whether two pages share similar page view in terms of the burst patterns, and if they co-burst, that usually means there's some association between these two events. So this sounds a very old idea because usually people tend to think that embedding representation is enough. So a bunch of us, Yuf, Goldberg, Dan, and Ido, back in 2019, we did a Dexterful seminar in El Caso. We tried to come up with some solutions to combine symbolic knowledge together with the embedding representation. So our idea is that since these two representations are really complementary, why? Because symbolic semantics are easy to manipulate. They're much more explainable, and we can easily order or compose them. And then for distributional semantics embeddings, we can use them for cross-lingual, cross-media transfer, as we already seen in the first session. And they allow us to do software decisions and software matching because they give us a very nice continuous embedding space rather than discrete. And they are more generalizable. So how to combine? From the examples we have seen so far, we can, for example, use joint entity and word embedding by changing the data format so that we can learn more embedding representation at the very first step. Or we can use graph neural network to initialize the representation using embeddings, and then we can update the representation using the semantic parsing results in the graph. Or we can use symbolic knowledge to improve the decoding, for example, using Schema to improve the IE decoding, as we have seen in the first session. And sometimes we also need to give a naming. For example, in schema induction, after you do clustering using embedding representation, maybe you can use symbolic distribution together to give a naming. And the whole idea is basically, let's try to do some injection using embedding features, and maybe we can do further knowledge reasoning using symbolic features. So the other direction, as we have seen from a lot of errors so far, is document level event injection. We haven't done enough, and I think that's a very promising direction to go. Basically, if we can aggregate the knowledge and information across the sentences that are showing related events, then we can enrich the embedding representation, and we can also find more arguments. For example, now the question here is, where was the person sentenced? So this is basically a sequence of events. They are all related, and as a human, we know that these events are involving the same defendant. That usually indicates the place is involved the same court in the same city because they happen in the similar time frame, and they share the same main character. And after that, before we can actually narrate the story, we will still need to verify the information, especially because of the information pollution problem. So here you can see, using similar sources, we can find very different views of the same events, even if the pictures look similar, but the event extraction results are completely different just because the sources have very different views. So we should combine our knowledge extraction with the source profile and some context, and then we can do fact checking, information consistency checking on knowledge element level, and then we can generate a more authentic narrative. Do some truth finding work. Okay, thank you. That's all. The next, Dan will continue talking about some grand vision. Thank you.
Hello again. So we're going to finish this tutorial with a bit more about our grand vision for event-centric natural language processing. And I'm going to start with a few more challenges that I think about as detailed event-centric challenges. And we'll start with time. So clearly representing time is essential for us to process events, reason about events. However, there's still a lot of open problems in how we represent time, what can we represent, and how can we map free-form text to representations that we can deal with. And you can just look at the examples on the right here, and I'm going to highlight a couple of them. The lion had a large meal and slept for 24 hours. What does that exactly mean in terms of the order of the events? And do we really mean exactly 24 hours? Or you can look at the next to last sentence that says the lion typically sleeps for 24 hours after having a large meal. So how do we interpret this and how do we reason about these kind of statements? But there are many, many other challenges in the area of time that we still don't have good formulations for. You can think about the following three examples. All of them have to do with something that happened in 1944. But if you read it, you see that even though we represent them in exactly the same way, it's just an interval that captures all of the year 1944, really the events should be represented in a very, very different way. US and Germany were at war throughout all of 1944. John got married somewhere in 1944 and perhaps stayed married throughout the rest of the year. And Jim was born on one date in 1944. We can also think about the informations that we get from temporal relations. So these two sentences talk about something that started before FDR took office. However, World War I not only started, but also ended before FDR took office. While the Great Depression started before FDR took office, this sentence really was written in order to mention, yes, while it's FDR responsibility to deal with the Great Depression, actually is not to blame for it because it started before he took office. So really the semantics of how we use this is very, very different. And I'm going to finish this with a couple other examples that illustrate the expressiveness or lack of many expressions where we use time. So in all these sentences, what you can see here is that we express time in various ways, but the semantics that we actually, as human readers, understand here is a lot richer than what we can do today with our formulations. So let me move to a second challenge that has to do with planning and reasoning about events. Quite often, reasoning about events requires that we plan around events and reason about implicit events, quantities, and time. Here are some examples. If we want to automate the question or answer the question, are we going to make it to dinner before the movie? Think about how many things you need to know and reason about in order to answer these simple questions. You need to know, of course, what's the time now and when is the movie, but a lot more than that, you have to know Where is dinner? What kind of dinner? What is a typical duration of dinner in the place I'm planning to go to? And maybe there are additional implicit events that you have to account for. Maybe parking next to the dinner place or next to the movie place should be taken into account too. And then I have to be able to put all these things together into an answer to this planning of a chain of events. And we can think about this guy, Aristotle. Did he have a laptop? So this is a funny question because it's clear to all of us that he didn't, but really there are several implicit events that we have to reason about in order to answer this question. So his time, his lifetime, or maybe the time he died. How is this relative to the time laptops were invented? Which one happened before? Very easy for humans, not so easy for us today because we don't even know how to decompose it in such a way that we recover the implicit events. And finally, quite often where we need to reason about events, we need to deal with quantities. So if you want to think about this fundraising event or election events, and it says more than 5 times the total raised by his 10 challengers combined, this is really an algebra word problem, and we have to be able to incorporate this into our planning too. My final example here is going to be from the area of grounding. Again, in order to reason about event, quite often we want to be able to we have to ground. We have to ground temporally or spatially or both. Sometimes this is a multimodal challenge. For example, if you see this picture, you probably know who this guy is. Do you know where it happened or when it happened? There's a lot of hints in that picture that probably are enough for some of you. How do we automate this? A sentence like this would raise the question of, what is this event? Where and when did it happen? And finally, if the visit to Berlin took place just before the collapse of the wall, it actually specifies time, but what is the event that we're talking about and where and when did it happen? So I want to finish with really grand vision challenges for this domain. And the first one has to do with reading books. Books are often about events, and you can think about a version of Cliff Notes that many of you are familiar with. And let's take David Copperfield's as an example. So this novel centered around David Copperfield, his journey of change and growth from the time he was born to maturity. As he meets many people, he changes his attitude toward many people, and he goes through multiple stages in his life. All this is fiction, and as human readers, we know that. But at the same time, the book happens with London and England in the 19th century as a background. And we learn a lot about the socioeconomic state in England of the 19th century, about child exploitation, about the high school systems, about prisons, about the emigration to Australia. These are all true historical facts. And as human readers, we can learn a lot from this book. So, but today we don't even have enough tools to distinguish between the fiction in the book and the true historical facts. So we could think about the computational tasks that we should develop in order to be able to support readers in reading these kind of books. And finally, I'm going to end with the process of the challenge of event reconstruction. So what I show here is a single frame from a really amazing reconstruction video that the New York Times put together for the killing of Breonna Taylor. The reconstruction was done by analyzing a lot of written evidence, transcript from interviews with witnesses, policemen, neighbors, analysis of physical evidence, that was collected at the scene, and it took weeks to produce. What would it take for us to automate this, or at least semi-automate it as a tool that would aid analysts? So instead of taking few weeks to do it, it will take them a day or a few days to do it. Ideally, we should be able, of course, to require some multimodal capabilities. We need to understand and reason about quantities, about geometry in this case. We need to reason about uncertainty because there's been a lot of evidence there, and some of it had to be pruned, some of it had to be weighted along with other information. And we also have to reason about possible conflicting events and possible conflicting reports. So we have to introduce also a notion of multiple perspectives with respect to events, trustworthiness with respect to the sources, and so on. So we are not going to develop such capabilities in the next few years, but hopefully this indicates how much potential there is when we try to think about natural language processing, and in this case, all of AI with an event-centric perspective. So with this, I'm going to thank you from all of us, and I'm just going to mention that the following few slides include pointer to some software and resources, and a lot of references that you may find interesting as you go over these slides. And hopefully there's going to be some time for questions now in the real presentation of this tutorial. Thanks.